periodic table of the elements is an arrangement, man-made, and the aim of this arrangement is to make easier the reading of the properties of these elements. And these properties are compared qualitatively and not quantitatively. In this figure, suppose they ask us to find or to compare the atomic size of the elements Al, Zn, In, Sn. So first of all, we have to write the electronic configuration. If the periodic table is not given, we have to write the electronic configuration in order to find their places in the periodic table. So we put these elements in the periodic table. Therefore, we can compare which has atomic size greater than the other. So this is a qualitative. The second property to compare between elements of the periodic table is the ionization energy, and the third property is the electronic affinity. First of all, what is the definition of the atomic size? The atomic size is the distance between the valence electron and the nucleus. And since the location of the electron, we said that the electron has no definite place. So the electron, for example, we said the electron is moving on the valence shell, and we know that the electron is found in one point where the probability of presence is maximum, but really we could not locate precisely the place of this electron. So the distance between the nucleus and the valence electron could not be measured. Could not be measured exactly. So what to do? For example, if we want to calculate the radius of atom X, we consider the molecule X2, and we suppose that these two atoms are tangent. So we have two nucleus, we have electron of the first and electron of the second, and this points the probability of presence. For molecule like Cl2, this is the X2 type, we can measure experimentally by X-ray diffraction method. We can measure the distance between the two nucleus. So this is the distance d. For any molecule, we can measure the distance between the atoms. So when the distance d is measured, and we supposed that X and X are tangent, so this distance is practically equal to the radius of the first plus radius of the second. So the distance in this case is equal to R, and R equal d over 2. This is the atomic size of the molecule X2. So the atomic radius is 1/2 the distance between two adjacent atoms in homonuclear diatomic molecule. In other words, we could not find directly the atomic size of atom X. We consider the molecule X2, we calculate the internuclear distance d, then d equal to R, so R equal d over 2, and the atomic size or the atomic radius is found indirectly. What is the ionic radius? The ionic radius is the radius of the ion of the corresponding atom, and we have difference between atomic radius and ionic radius since the number of electrons are different. Our objective is to know the trends in atomic size. That means what is the order of change in the same period, in the same row, or in the same column, in the same group. The atomic size in the periodic table increase from. So the size increase going down a column. So the size increase from up to down. Why the atomic size increase? This is very simple. Hydrogen is in unequal 1. Lithium is in unequal 1 and by lithium is an unequal 2. Sodium is in unequal 3. So the electronic configuration of hydrogen ends by 1s1. Lithium 2s1. Sodium 3s1. Potassium 4s1. And we know in the quantum numbers, as an increase, the volume of the orbital increase. And the volume of the orbital increase, that means we have more points of probability of presence. So as up to down, this is logic to say that the radius increase. So as a conclusion, in the same column or in the same group, the atomic size increase from up to down, or we can say in the same group or the same column, as Z increase, the atomic size increase. So this is the trend in the column. What is the trend in the period? In the same period or in the same line, as Z increase, the atomic size decrease. So in other words, in the same period or in the same line, the atomic size increase from right to left. From right to left in the periodic table. So now how to compare the atomic size of elements? First of all, we put these atoms in the periodic table. We know their places. Then we say in the periodic table, the atomic size increases from right to left, from up to down, and therefore we can compare qualitatively their atomic size. I will prove now why in the same period or in the same row or in the same line, the atomic size increase from right to left. In a row, the same number of shell, the size decrease when the number of electrons core increase. I will consider the example of sodium and that of magnesium. Sodium has the electronic configuration 1s2, 2s2, 2p6, 3s1. Magnesium 1s2, 2s2, 2p6, 3s2. So the sodium is in the third row, group 1, and the magnesium is in the third row, group 2. So by theory, the atomic size, the place of the sodium is in this point, and the place of magnesium is in this point. So the radius of the sodium is greater than the radius of magnesium. I will explain this proof, but for you, you can apply directly the trend without this proof. It's not necessary to make this proof to compare the radius in the same row. So the objective now is to prove that the radius of sodium is greater than the radius of magnesium. First, in the first sodium, we have 11 protons. In the magnesium, we have 12 protons. In the sodium, we have 10 core electrons. In the magnesium, we have the same number of core electrons, 10. And in sodium, we have 1 valence. In magnesium, we have 2 valence electrons. In sodium, we have 3 shells. So the electron configuration ends by n equal 3. And in case of magnesium, we have also 3 shells. The first view, if we look to sodium and magnesium, we can say that sodium and magnesium have the same atomic size, since the number of shells are the same. But I ask, what is the forces that affect the valence electron in sodium? And the same question for the 2 electrons in magnesium. The valence electron in sodium is submitted to Coulomb attraction force F equal K constant times the Q, which is the charge of the nucleus 11, times the Q prime, which is 1, divided by the distance square between the nucleus and the valence. So the valence electrons in case of sodium and magnesium are affected by the Coulomb attraction force that depend on the charge of the nucleus, the charge of the valence electrons, and the distance between the nucleus and the valence electrons. So as first approximation, we can say that sodium and magnesium have the same D. This is the first approximation. So the factor that affect the force are the charges QQ prime. As QQ prime increase, the attraction force increase, so the electron is more attracted by the nucleus, so the radius decrease. So I have to compare now QQ prime in case of sodium and the QQ prime in case of magnesium. In case of sodium, I have 11 times 1 equal 11. In case of magnesium, I have 12 times 2 equal 24. So the attraction in magnesium is greater than the attraction of sodium. Therefore, the radius of the sodium is greater than the radius of magnesium. What is the meaning of greater attraction? Greater attraction means the electrons are more attracted by the nucleus. So the distance between the nucleus and these electrons decrease. So I proved why sodium has a greater radius than magnesium. I can use this rule if Z of the elements are different. In sodium, Z equal 11. In magnesium, Z equal 12. So this rule can be used. What would happen when we have the same Z? If we have the same Z, this rule could not be applied. For example, Cl and Cl minus. I compare the radius in Cl and the radius in Cl minus. The first Cl has Z equal 17. The second Cl has Z equal 17. So this rule I proved here could not be applied in this case. We have to apply another rule, is to look the number of protons that affect one valence electron. For example, compare the radius in X having atomic number Z and X prime. We know that X prime have the same Z of X. So the previous rule to compare Q prime could not be applied. So what is the rule that can be used? First of all, I count, for example, I have 11 protons and I have 11 electrons. In the second, if Z equal 11, I have 11 protons and X is obtained from X minus is obtained from X by adding 1 electron. So if I suppose that the first has 11 electrons, the second has 12 electrons. So X and X minus have the same Z, so the same number of protons, but different number of electrons. If I use Q prime, no, since Z is the same. So what to do? What is the second rule? For same Z, look to the number of protons affecting the valence electrons. In the first, X and the second, X prime, have the same core electrons, 10. In X, I have 1 valence. In X primes, in X minus, I have 2 valence. So in X, 1 electron is attracted by 11 proton. 1 electron is attracted by 11 proton. In X minus, I have 2 valence attracted by 11. So 1 electron is attracted by 11 over 2 is attracted by 5.5 plus. I will repeat. If I want to compare the radius of 2 species, I can use the rule F equal KQ prime divided by D square. If these 2 elements to compare are in the same row, so practically they have the same distance D. So the factor that affects the attraction is a QQ prime. Okay? And this is the rule 1. Suppose I want to compare now X and X prime. X and X minus. X minus is the ion of X. But X and X minus have the same Z. So rule 1 could be applied. What to do? Is to look the number of protons per 1 valence. In the first, I have 1 attracted by 11. So the attraction is 1 to 11. In the second, I have 2 attracted by 11. So 1 is attracted by 5.5. Compare the attraction. In the first, 1 valence attracted by 11. In the second, 1 valence attracted by 5.5. So the attraction in X is greater than the attraction in X minus. And in this case, the radius of X is less than the radius of X minus. This is the trans in atomic size, or the comparison between atomic size of atom and ionic size of ion. What are the trans in atomic radius for transition metals? The 2 rules I mentioned before, rule 1 is to compare QQ prime when Z are different, or is to compare the number of valence the number of 1 valence or the attraction of 1 valence per number of protons if Z are different. These 2 rules are applied for block S and the block P. So what are the trends in atomic radius for transition metals? For transition metals, the atomic size increase down the group. So that in the same column, the atomic size of transition metals increase from up to down. Now in the same row, the atomic size or the atomic radius of transition metals are practically or have practically the same size across the D block. So in the row, the atomic size, in the same row, the atomic size of transition metals are practically the same. In the same column, the atomic size increase from up to down. Magnetic properties of transition metal atoms. So I finished the atomic size. Now I will compare another property in the periodic table, the magnetic properties of transition metal atom and ions. What is the magnetic property? Suppose I have atom X and they ask if this or what is the magnetic property of X. First of all, I write the electronic configuration. If the electronic configuration contains at least one single electron, so this atom is paramagnetic, and that means it will be attracted to a magnetic field. And if the electronic configuration did not contain any unpaired electron, it contains only pairs of electrons, so the electronic configuration is saturated. In this case, we say that this atom is diamagnetic. What is the meaning of diamagnetic? That means slightly repelled by a magnetic field. For example, if I write the electronic configuration of Ag, krypton, 5s1, 4d10, the core electron is completely filled. Why? Because we cannot fill level 5 if the core electrons is not completely filled. If we look to the electronic configuration 5s1, 4d10, we have one single at 5. If electronic configuration contains at least one single, so Ag is paramagnetic. Write Ag plus from Ag. We have to remove one electron from outer shell. We remove 5s1, so we obtain a krypton 4d10. We don't have any single in this electronic configuration, so Ag plus is diamagnetic. Suppose they ask for Ag2 plus, so we have to remove another one electron. Now we have to remove from D10, so we obtain 49. If we write the box representation of 49, we can see that we have single electron, so Ag2 plus is paramagnetic. So in this session, we studied, as a conclusion, we studied two properties. The first is the atomic size. The atomic size increase in the periodic table from right to left, from up to down. Second, we compare the atomic size of atom to its corresponding ion, for example, X and X minus. And we use the rule 2, X and X minus have the same Z, so we have to compare the number of protons per one valence electrons, and we proved that the attraction in X is greater than the attraction of X minus, so the radius of the atom is less than the radius of the corresponding anion. Second, we studied the magnetic property of atom. And to study this magnetic property, we have to write the electronic configuration. In the electronic configuration, if we have at least, we can have more than one, but at least we need one. If we have at least one single electron, so we say that this element or this atom is paramagnetic. Paramagnetic means it will be attracted by a magnetic field. And if the electronic configuration did not contain any single, it contains only pairs of electrons, so we can say this is diamagnetic, and the meaning it's slightly repelled by a magnetic field.